All right, chapter 17. So, chapter 17 is kind of a continuation of the acid and base unit that we just did. So, a lot of this stuff is going to piggyback on what you did last week. So, let's jump in with that as soon as I get a pen here. Oh, let's see, pen color. Let's go with blue today. All right, there we go. So, first, let's look at equilibrium as it pertains to a weak acid, right? So we have acetic acid. It's a weak acid. We can identify that from a lot of different ways, but the easiest one is probably that equilibrium arrow right there. And when we look at sodium acetate, we say, all right, well, that's a strong electrolyte, right? We have a yield arrow just pointing in one direction. We have complete dissociation. We know that um, sodium acetate here is completely dissociated. And so if we have acetate from sodium acetate in a solution of acetic acid, then the equilibrium of this um, solution is going to shift to the left. All right. And when we look at that, we might go, all right, well, wait a minute. How do I know that? How can I spot that? So there's something called the common ion effect. All right. And the common ion effect is what we're looking at in that opening problem there. And the common ion effect says this: if you have a weak electrolyte and a strong electrolyte together in the same solution, and they both have a common ion. So in this case, we have CH3COO minus, that acetate ion, and we have it here again. So there's our common ion. When they are together in solution, the weak electrolyte will ionize less than it would if it were alone. All right. And so that's going to affect acids and bases when they're in equilibrium together, okay? And later on in this chapter, we'll also see how it affects solubility. But the first thing we want to look at is equilibrium. So here we've got a question, right? It says, what is the pH of a solution made by adding zero point 0.3 moles of acetic acid and zero point 0.3 moles of sodium acetate to enough water to make a 1 liter solution? Well, if we just start with our acetic acid, right? So this is acetic acid. We know by this point, right, in order to do an ice table, we need to write our equation, and then we need to write our expression, and then we need to fill in our ice table. And we know that when we're doing it with um, our, like, starting at, time equals 0 and all that other jazz, how to fill that in, right? So we're using the X. We're going to use algebra to solve this. We've done this a couple times. So hopefully this screen makes sense. So we look at it and we say, all right, well, our Ka based on this information is going to be 1.8 times 10 to the negative 5. And we're going to plug in our x's. We're going to solve that. Remember that we're going to assume that taking x away from 0.3 is not going to change the 0.3 a whole bunch. So we just leave it at 0.3. And we can figure out our pH here is going to be 4.74. So when we look at this, we're like, all right, well, how is this different from our common ion example? Well, notice that this one over here isn't starting at 0. All right. We know we've got 0.3 moles of acetic acid and we have 0.3 moles of sodium acetate. So we write our equilibrium expression, or sorry, our equation for the weak acid. So here is our weak acid um, equation. And we write the Ka for the weak acid, all right, just like we did before, all right. But over here on the right, this is where the common ion comes into effect. Common ion. Because we have 0.3 moles of sodium acetate. So that is where I have to be able to spot, oh, there's a common ion there. So in all the ones that we've done up to this point, the starting number here was 0. And this was just, plus XM, and, you'd end up with, because there was a 0.3 there. So now we have or there was no 0.3 there, rather. So now we have to know, oh, drop the common ion in and and that's what will account for the common ion effect. All right, so there we go. That's what the example looks like. Now, when you mix acids and bases, it's important that we take a moment to look at buffers. And buffers are a solution that's comprised of this conjugate acid-base pair. And when you have a buffer solution, it's going to resist changes in pH. Now, a lot of times they have really high concentrations of both the acid and the base present. They're usually in approximately equal concentrations. And in order to make a buffer, it's actually pretty simple. You need to mix a weak acid and a salt of its conjugate base, or you need to mix a weak base and a salt of its conjugate acid. That's pretty much what you do. The other way you can do it is to add a strong acid to a weak base in order to partially neutralize it, or add a strong base to a weak acid to partially neutralize it. And what that's going to do, wrong way, is create a solution that has some extra, like bufferable, for lack of a better word, components in it. And so when you have your initial buffered solution, so look at this picture here. Here's our initial buffered solution. And in this one, we're using HF. So the concentration of HF is equal to the concentration of F minus. So if I add some acid, right, we're going to add acid. Well, there is a little bit of F minus in solution, right, because that concentration is there. And that's going to counteract the addition of that hydrogen, right, because the F and the H plus are going to give us HF. And so instead of going all the way up here, right, you're going to have this nice, buffered solution, right? It's going to resist the change, the drastic change in pH. If on the left here we add a base, right, well, the presence of the HF, right, which is going to slightly ionize and give you a couple H pluses, is going to prevent this from drastically increasing the pH, right, making it more of a basic solution. The basic understanding of a buffer is if you have a buffered solution, you can add a little bit of acid or base to it with less of effect than normal. Now, we do need to be able to calculate the pH of a buffer. And so if we look at the weak acid Ka, we know that we do the concentration of hydrogen times the concentration of our anion over the concentration of the acid. If we take the negative log of both sides, right, because if we do something to one side, we do it to the other, and rearrange it, we get this equation right here. Negative log of H plus equals negative log of Ka plus the log of A minus over HA. Well, we know that the negative log of H plus is pH, right? We know that the negative log of Ka is pKa. And so the pH equals the pKa plus the log of the concentration of the anion over the concentration of the acid. And there's a name for this equation. It's called the Henderson-Hasselbalch equation. You need to know it. It only applies to buffers. That's the only time you'll use it. But this is the formula we use to calculate the pH of a buffer. So here's a question for you, right? What is the pH of a buffer that is 0.12 molar in lactic acid? And there's CH3, CHOH, COOH, so there's a carboxylic acid in there, and 0.1 molar in sodium lactate. The Ka for lactic acid is 1.4 times 10 to the negative fourth. All right, well, I'm just going to plug in my Henderson-Hasselbalch equation, right? So I need to find pH. So I need to find the pKa. Well, the pKa is negative log of the Ka. So here is the Ka. So it goes right there, Ka. And then I have the log of my anion, the 0.1 molar, over the acid, 0.12 molar. Easy, right? Punch it into your calculator, be done. Remember, if you don't have a calculator, we can do the approximation, where here we would have 1.4 minus 0.4, which would give us approximately 1. And so, wait, no, hold on. Yeah, no, that's right. So there we go. We could do that without the calculator. All right, what is buffer capacity? Well, the amount of acid or base that the buffer can neutralize before you start to have a real drastic swing is called the buffer capacity. And if you look at the Henderson-Hasselbalch equation, the pH is going to be the same, all right, for each conjugate acid base pair of 1 molar each or 0.1 molar each, all right? So that's how they're going to go together. If you have a buffer that is 1 molar, it can neutralize more acid before the pH changes, right? The stronger the molarity of the buffer, the more acid or base it can neutralize before your pH is going to change. Now, when we look at buffers in specific instances, like buffer X or buffer Y, there's going to be a pH range over which that buffer is going to be effective. The optimal pH, right, is going to be the pH at pKa, where the HA and the A minus, the anions concentrations, are equal to each other. If one concentration is more than 10 times the other, that means the buffering action is poor. So you can usually like rule of thumb it as 1 pH unit from pKa is going to be the buffer range. And the reason we can do that is because remember that to go from 1 to 2 on the pH scale is times 10, right? That's the acidity. And if you did from 2 to 3, that would be times 10. So from 1 to 3, you would be times 100. So since 10 times is about the limit, that's where the buffering action starts to break down. If we just say plus or minus 1 pH unit, we're looking at it as a magnitude of 10. Now, if we add a strong acid or a strong base to a buffer, then we can use stoichiometry in order to calculate, any of the outcomes of a neutralization reaction, just like we normally would. Again, when we do this, right, we need to use the Henderson-Hasselbalch equation to find the pH. Right, so we'll do a stoic calculation, and then we'll do an equilibrium calculation. So let's look at one of those. So we have a buffer. It's made from 0.3 moles of this acetic acid and 0.3 moles of, let's see, that would be sodium acetate, to enough water to make 1 liter of solution. Calculate the pH after 1 mole of sodium hydroxide, or sorry, 0.02 moles of sodium hydroxide is added. So we're going to use a version of the ice table, right? We have initial change and then equilibrium normally. So now we're going to have before the reaction, the change, and then the after the reaction. So we know we have 0.3, all right, of our acid because we have 0.3 molars or moles there. We know we have 0.3 of our common ion there on the right, our acetate. We know that at the end, okay, we're going to add during the reaction, our change, we're going to add 0.02 moles of sodium hydroxide. All right. We're going to then, right there, that's going to make these blanks, like we can fill those in, right? So we added 0.02, so these must be negatives. And then we just do final minus initial, right? So 3 plus 0.02 is 0.32. And over here we have 0.3 minus 0.02, so we have 0.28. We plug in our Henderson-Hasselbalch equation, right? We know that in the buffer, the volume of each concentration is about the same. So we're going to use that ratio of molarity in order to calculate our ratio of moles. So we have N, right, where this is the number of moles of HA over the N of the A minus. So 4.74, there's our pKa, plus the log of 0.32 over 0.28 gives us 4.8. And there we go. All right, so let's switch gears a little bit. If you need to pause it, go back, rewatch, take a break, that's fine. All right, we got quite a busy week this week, so if you need to take a break, take a break. And then we'll start with titrations. All right, so in the second video, we'll pick up here and keep on getting it. All right, if you have questions about the first part, let me know, and I'll be glad to give you guys a hand.